Hi there, this is Jize presenting our output of COMP9043 research project. We have been working on the topic of proof of implementation, which belongs to the experiment track. Now let's begin. First, let me introduce briefly the proof of algorithms to you. They are essentially a group of consensus algorithms which help make determinations over a distributed system. Consensus algorithms are the spirit of blockchain technology, and in the context of blockchain, the use of consensus algorithms can verify that the information being added is valid. After all the nodes achieve the consensus, a new block will be appended to the blockchain, and then the information stored at each node is updated. However, such a system can be ruined by replay and forgery. To protect the whole network from security attacks, the consensus algorithms should be robust by implementing cryptographic techniques. And as you can see, there are some most known proof of algorithms, such as proof of work, proof of stake, delegated proof of stake, and practical Byzantine fault tolerance. There are also some less known ones, most of which are created specifically for different blockchains. Well, because of the restriction of time, in this video we only introduce PBFT algorithm, and the information of POW, POS, and DPoS can be accessed in our article. Now comes the PBFT, Practical Byzantine Fault Tolerance. It is very suitable for a consortium blockchain applied by Hyperledger Fabric. Hyperledger Fabric is a famous consortium blockchain developed by IBM. The PBFT algorithm tolerates less than 1/3 of malicious or faulty replicas. That is, suppose there are 3 f+1 replicas in total, then the maximum of faulty node is f. And it also makes use of multiple cryptographic measures, such as public key signatures, MAC, and the message digest by hash functions. Here is the basic 5 stages of PBFT mechanism. As we can see, C is the client who sends the request, and validators O1 to 3 are all replicas of a node, where O is named the primary replica and others are backup replicas. The first stage is request, where client C sends a request to the primary 0. And then comes the pre-prepare stage, where primary 0 receives the request from C and multicasts it to backups, that is, the 1, 2, and 3. And in the prepared stage, replicas execute the request and then rebroadcast to the result to each other, that is 1 to 0 to 3 and 2 to 013. While replica 3 is unable to broadcast due to the fault. Then we come to the commit stage. After receiving the certain number of identical requests in the prepare stage, replicas broadcast the commit to each other. This guarantees the validity of the result because of the tolerance ability. And we come to the last stage, reply. Each replica gives feedback to C if it has received a certain number of identical requests in the commit phase. Here comes some key points during the implementation of PBFT. First, the generation and verification of RSA signature. Here we directly use the RSA package provided by Go language. Go is a very friendly language to the cryptographic development. We use MD5 hash function and some sort for message digest. After the primary replica receives the message in a pre-prepare stage, it verifies the signature before rebroadcasting. Let's have a look at the code. Yeah, here is the RSA signature generation method, and we use MD5 here and add some sort here. In the pre-prepare stage, we just call this method to verify the RSA signature. If there is indeed an error, it won't rebroadcast the message to the next stage. And the RSA signature is only used once in our program according to the original paper, because it is very time consuming. In the following stages, we replace it with MAC. And the second issue is the generation and verification of MAC. We achieved the generation of MAC by simply calling the corresponding API in Go, and we use SHA-256 as the hash function in MAC mechanism. If you want to check the MAC on the other node, just use the same session key to generate a new MAC and compare it with the expected MAC. Let's have a look. Here are two very simple functions of generating and checking MAC. And if we want to rebroadcast the message with MAC, let's see. Yeah, here. Just simply call the generate MAC with the session key. And in terms of the message broadcasts through replicas, we use HTTP GET at the request stage and use HTTP POST at the other stages. In addition, here's a big simplification where all nodes are sharing the same session keys for MAC and key pairs for RSA signature because of the tedious requirement of a forehand key distribution. Now let's have a look at the actual output of the algorithm. We are starting 4 nodes. The 1110 is the primary replica and the other 3 are the backup replicas. Now they have been started and we go to the client. The browser is acted as a client. We send a message to the replicas. The message is hello world. And you can see the 3 authentication successful messages are received from node 1 to 3. Here we can see the printed logs from each node. So in order to check the tolerance feature of PBFT, we kill one of the nodes to see whether it still works. For example, we kill PBFT 1113. It should work. We send the request again. You can see the successful message are still returned. Because if there are 3f plus 1 replicas in total, here is 4, then the maximum of 40 nodes is f, here is 1. So if the 40 node is more than 1, there shouldn't be any successful messages. We can check by killing 112. Now we re-request again. The client received nothing, so this demonstrates the mechanism is successfully implemented. Now that we have gone through several demos of our consensus algorithms, we have demonstrated the rationale and mechanism of common proof-of algorithms, and we have achieved simplified implementation of POW, POS, DPoS, and PBFT in Go language. However, there are lots of things to be done further to improve our study, including bringing out practical distributed structures and perfecting the cryptographic processes. And that's basically all of our general work. Thanks for your listening.